Hey, Screen Distiller. I did a video on dynamic programming theory, so now I think it's a good idea to tackle the implementation. I found a competition on AdCoder with a bunch of easy DP problems, so let's take a look. Here's the first one. It's called Frog 1. In the problem setup, there are n stones numbered 1 to n. Each stone has a height hi, and a frog is initially on stone 1. The frog can jump to the next stone or the stone after the next stone, so stone i+1 or i+2. And when the frog jumps, it incurs a cost, which is the absolute value of the differences of the heights of those stones. And you want to find the minimum possible total cost for the frog to get from stone 1 to stone n. So let's try to formulate the subproblem, state, and recurrence relation. So the subproblem is, given that I'm on stone I, what is the minimum cost for me to get to stone n? So you can see that if we have the answer to the subproblem for I equals 1, we have the answer to the whole problem. Also, it's possible to construct the answer to the subproblem from the answer to smaller subproblem. So let's look at the recurrence relation. If I'm at stone I and I know what the best answer is from stone i+1 and stone i+2, then I can compute what's the better stone to jump to by looking at the difference in heights between my current stone and stone i+1, or my current stone and stone i+2. So that difference plus the cost to get from stone i+1 or i+2 to stone n, choosing the best out of those two is going to be the recurrence relation. And for the state, all we need to know is the stone that we're currently on. So we end up with a DP that has a state that contains where we currently are, that's n values, and it just checks the next stone or the stone after that. So that's a linear time DP, and n is 10 to the 5, which fits really easily into the time limit of 2 seconds. So let's try coding it up. So first trick, this header bits/std++.h, that just includes all the headers that you want, so you don't have to waste time writing a bunch of random include statements. All right, so let's deal with the input first. I like to store my DP tables in global memory because it means it can be accessed from anywhere and it gets initialized to 0 when the program starts, which is sometimes useful, sometimes not. I've also added 5 to max n here. And the reason for this is that you see in this problem, everything's 1-based. So if we decide to do things 1-based, which I think I will, if we indexed by n into a DP array, we'd actually be indexing past the end of the array if we made the size of that array equal n. So here I just make a max n plus 5 just to deal with any off by 1 errors. At least you're accessing within memory that exists, and instead of your program getting a runtime error, it may get AC. Let's deal with the rest of the input. I'm using C style input rather than C++ style input. Most of this is just force of habit, but C input can be faster than C++ input. This shouldn't make a difference in most problems, but if the problem has a lot of input and you're getting TLA, it might be because of the speed of input, maybe. So here's another trick. I wrote heights plus I here instead of ampersand heights left bracket I right bracket. This is a lot easier to type and save you some keystrokes and a small amount of time. This is just doing pointer arithmetic rather than array indexing and then taking the pointer to that. Now we need to write the DP. Let's put in the memorization array. Since our state is just which stone we're on, this is just an array of size n. Or max n, I just initialize everything with the maximum value. Then you don't have to worry with using vectors, which can be slow. They have an initial layer of indirection. Just initialize everything to max n, and then you can use a bunch of static arrays. Sometimes it's nicer to use vectors. I prefer doing it this way. There are people who do it both ways, so choose whichever way you prefer. All right, so we've got our DP. Let's write the recurrence relation. First, we need to take care of the base cases. If we're at stone n, then we've done it, and the cost to reach the stone n is 0. Also, it's possible to get to a stone past n if we're on stone n take 1 and then we jump to stone i+2. In this case, it's not like a valid thing to do, so we just want to return some sentinel value. So let's define some max value. I made this 2 billion. If we look in the problem statement, you can see hi is up to 10 to the 4 and it's positive, which means that in the worst case, we'll jump 1 stone forward each time and we'll add 10 to the 4 each time. We'll do that 10 to the 5 times. So 10 times 5 times 10 to the 4 is 10 to the 9. And here we've got 2 times 10 to the 9. So this is going to be higher than any possible answer. So if we return this, there's no chance that it's going to take the place of an answer we actually wanted and give us a wrong answer. Now we just need to check our memory. So let's initialize this to a sentinel value. Let's say -1. This memset here is a little tricky. So memset actually only sets byte values. This -1 here, the only reason this works is because -1 is all ones in binary, which means that whether memset would set 1 byte or 4 bytes, it's not going to make any difference to the actual answer. This is a kind of tricky way to set everything in mem to be -1, even though mem is not composed of just chars. You can only really do this for like -1 and 0. 0 is all zeros, -1 is all ones. So those are the two easy values to do this with. So now we just check if this has been put in the DP array before. The costs are always greater than or equal to 0. So if it's -1, there's no chance that could be a real answer. So that's why I'm using -1 as a sentinel value. So now all we need to do is try hopping to stone I+1 or stone I+2. Since we index into heights here, we actually have to check this bounds here anyway. Even though we did this, but I just check the bounds before I do it and try going to stone I+1 and adding the cost for doing that. And then I try the other case, which is going to stone +2 and add the cost for that. Then I make sure to set the value here. If we don't do this, we'll end up just doing like a DFS and recursively doing a bunch of stuff, and it'll be exponential time. Doing this set into the memorization table here is what makes it faster. And now all that's left is just to print out the value. Oh, and here's a tricky bug I just realized. We actually need to do +1 here because we're doing 1 indexed. I should have just done it 0 indexed, hey. But we're doing 1 indexed, so we need to make sure that when we read height stone, it gives us, if we do heights 1, we want that to actually give us the first height value. So we need to add 1 here. Or alternatively, we could change this to 1 and make this less than equals. Okay, so let's try it out and see if it works. Okay, it prints -1, which is not right. So, yeah. This should be not equal to -1. Okay, that's right. That's correct. Okay, that's correct. Let's YOLO submit this. I don't recommend doing this, but it passes the sample input, which means that it must pass all the input, right? Well, let's see. Okay, correct. That was frog 1. We did frog 1, here's frog 2. The setup for the problem is basically the same. N stones numbered 1 to n, and each stone has a height. The frog is initially on stone 1, and he will jump to one of the next k stones. So in frog 1, jump to one of the first 2 stones, he will jump into one of the first k stones, and the cost function is the same, and we got to output the same thing, the minimum possible total cost. K is 100, which means that instead of in the recurrence relation, we just have trying the next stone and the stone after that, we can just try all the next k stones, and 10 times 5, 10 to the 5 times 10 to the 2 is 10 to the 7, which is definitely going to run in time. As a general rule, you can do about 100 million operations in a second. 100 million fast operations, like maybe 50 million slower operations. 100 million is 10 to the 8. So 10 to the 7 is well within the bounds of this problem, which is 2 seconds and 1 gigabyte of memory. So let's start off by copying the contents of frog 1, because it's probably going to be pretty similar. We just have to deal with doing k things instead. So we just got to change this part of the recurrence relation. So let's do that. So we want to start at the next stone from where we currently are and try the next k stones. Now we got to make sure that we don't go past the end of the array. So let's just do a quick check. Otherwise, we want to try computing what the best possible value would be if we jumped from our current stone to the ith stone. Okay, so this should be it, I think. Oh, we got to read in k. I forgot about that. All right, let's try it out. All right, first sample input. That's correct. That's correct. That's correct. That's correct. Yeah, let's YOLO submit it again. All right, AC, that's frog 2. Now I know what you're all wondering. Is there a frog 3? Turns out, yes, there is a frog 3. I had a look at it and had a bit of a think, and it looks significantly harder than frog 2. It seems like you have to do some like weird convex hull optimization, like inequality thing. And we're just doing basic DP stuff today. So let's move on to this problem, vacation. So the setup is person has a summer vacation. Vacation has n days, and each day the person chooses one of 3 activities, A, B, and C. They get some amount of points based on which activity they do, and they can't do the same activity for 2 or more consecutive days. So this is DP again. We want to store which day we're at. We also need a way to make sure that we don't choose the same activity twice in a row. What we can do is store the previous thing we did on the previous day. And there's just one special case with this. On the first day, we can choose anything, either A, B, or C. So in that case, we need a special value that just says this is the first day, or we didn't like pick an activity yesterday or something like that. The subproblem is, given that I'm on the ith day and yesterday I did this activity, what is the maximum total possible points that I can get? And the recurrence relation will be, if we didn't do A yesterday, try A, see how many points that gets us. If we didn't do B yesterday, try B, see how many points that gets us, etc., and take the maximum of all of those. Okay, so let's try coding it up. Let's quickly do input. Okay, now let's define our DP array. Now here in our state, which day we're on is the first item of the state. The second item is the activity we did previously. So we don't have 3 here, we actually have 4 things, because on the first day we can choose any activity. So I'll just make another like fake activity, D, which is like, you can do whatever activity you want on this day, and we'll only use it on the first day. We're on the day, and we chose prev as the previous activity. And I'll assign A to be activity 1, B to be activity 2, C to be activity 3, and 0 to be the sentinel activity, as it were. So let's do the base cases. Let's index day from 0, which means that if we get to day equals n, we've gone through all of the days, and we can just return 0. Unlike the frog problem, we don't have to worry about skipping past n. So we need like a day greater than n case, because we only go forward 1 day at a time. So we're guaranteed to hit n. And in that case, we safely made it through all the vacation days. So we just return 0 for that cost. And this is just the standard checkout table to see if we've already computed this value case. Now we need to go through the 3 activities and see which ones we can do and choose the best one. Here I've added if statements that check if we reuse the same activity twice in a row. We'll go to the next day, and if we chose A, we say we did A previously, and then we add on the number of points of happiness, or whatever they called it, for taking activity A on this day. And then we save it and return it at the end. So to get the answer, remember our subproblem is, given we're on the day, and we took this activity previously, what is the highest points we can get? Well, we just call it with starting from the 0th day, and we did no activity in the previous day. What's the best answer we can get? And if we just print this out, this will be the answer. At this point, it's worth checking that the value we compute is never going to exceed the size of a 32-bit integer. So the worst case for getting a really big total points of happiness is every day we get an extra 10 to the 4, and we do that 10 to the 5 times. So that's 10 to the 5 times 10 to the 4, 10 to the 9. And that's fine. It stores up to 2 times 10 to the 9. So let's try this out. Okay, that's correct. All right, that's correct. That's correct too. All right, let us YOLO submit once again. Okay, correct answer. That was vacation.